colloids and colloidal systems, optical, kinetic, electrical properties, and applications. Colloid science is an important interdisciplinary field involving chemistry, physics, biology, materials science, and engineering. Colloidal systems consist of finely divided particles dispersed in a continuous medium, with particle sizes typically ranging from 1 nanometer to 1,000 nanometers. These systems occupy an intermediate state between true solutions, in which dissolved species exist at the molecular level, and suspensions, in which particles are sufficiently large to settle under gravity. The distinctive behavior of colloids arises primarily from their large surface area to volume ratio and dominant interfacial phenomena. As a result, colloidal systems exhibit characteristic optical, kinetic, and electrical properties that differ significantly from those of bulk materials. Colloids are widely encountered in natural and industrial systems, including milk, blood, paints, pharmaceuticals, aerosols, detergents, emulsions, and inks. A colloidal system contains two phases, the dispersed phase and the dispersion medium. The dispersed phase consists of colloidal particles, while the surrounding continuous phase serves as the medium in which they are dispersed. Depending on the physical states of these phases, colloidal systems may exist as sols, gels, emulsions, foams, or aerosols. Their stability depends strongly on particle interactions, surface charge, temperature, and the properties of the surrounding medium. Historical development of colloid science. The foundations of colloid chemistry were established in the 19th century by Thomas Graham, who studied the diffusion of substances through semi-permeable membranes. Graham observed that substances such as sodium chloride and sugar diffused readily, whereas gelatin and starch diffused slowly. He referred to the latter group as colloids, derived from the Greek word kolla, meaning glue. Later investigations showed that colloidal behavior depends primarily on particle size rather than chemical composition. Any material can exhibit colloidal properties if divided into sufficiently small particles. Important contributions were subsequently made by Richard Zsigmondy, who developed the ultramicroscope for observing colloidal particles, and Albert Einstein, who theoretically explained Brownian motion using kinetic molecular theory. The development of electron microscopy, surface chemistry, and polymer science during the 20th century significantly expanded the understanding and applications of colloidal systems. Nature and classification of colloids. Colloidal systems are heterogeneous because they consist of two distinct phases, although they often appear homogeneous to the naked eye. Colloidal particles may possess spherical, rod-like, fibrous, or plate-like structures. In many cases, only one dimension of the particle needs to fall within the colloidal size range. Colloids are commonly classified according to the physical states of the dispersed phase and the dispersion medium. Solid particles dispersed in liquids form sols. Liquid droplets dispersed in another liquid form. Emulsions, gas dispersed in liquids produces foams, and solids dispersed in gases form aerosols such as smoke. The stability of colloidal systems results from the balance between attractive and repulsive forces acting between particles. Although colloids are thermodynamically unstable due to high surface energy, they often remain kinetically stable for long periods. Optical properties of colloids. One of the most important optical properties of colloids is the scattering of light, known as the Tyndall effect. When a beam of light passes through a colloidal dispersion, the path of light becomes visible because colloidal particles scatter the incident radiation. In contrast, true solutions do not scatter light significantly because dissolved molecules are too small. The Tyndall effect explains several familiar phenomena, including sunlight passing through fog, visible beams from vehicle headlights in dusty air, and the blue color of the sky. The intensity of scattering depends on particle size, concentration, and wavelength of light. Smaller particles preferentially scatter shorter wavelengths. The optical behavior of colloids also forms the basis of ultramicroscopy, where scattered light from colloidal particles appears as bright spots against a dark background. Although the actual particles are not directly resolved, ultramicroscopy enables observation of particle motion and distribution. Modern characterization techniques such as transmission electron microscopy and scanning electron microscopy provide direct information regarding particle morphology, aggregation, and size distribution at nanometer resolution. Kinetic properties of colloids. The most significant kinetic property of colloids is Brownian motion, which refers to the continuous random movement of colloidal particles suspended in a fluid. This motion was first observed by Robert Brown in 1827. Brownian motion arises from the unequal bombardment of colloidal particles by rapidly moving molecules of the surrounding medium. Einstein later provided a mathematical explanation based on molecular kinetic theory. The random movement of particles counteracts gravitational settling and contributes significantly to colloidal stability. The diffusion behavior of colloids is described by the Stokes-Einstein equation, D equals kBt divided by 6 pi eta, where d is the diffusion coefficient, kb is the Boltzmann constant, T is the temperature, eta is the viscosity, and r is the particle radius. Smaller particles exhibit more vigorous Brownian motion because molecular collisions exert a greater relative influence on them. Brownian motion provides important evidence for the molecular nature of matter and plays a critical role in diffusion, particle transport, and colloidal stability. Sedimentation of colloidal particles occurs very slowly because Brownian motion offsets gravitational effects. Consequently, many colloidal dispersions remain stable for extended periods without settling. Electrical properties of colloids. Most colloidal particles acquire an electrical charge when dispersed in a medium. Surface charge commonly develops through preferential adsorption of ions or ionization of surface groups. The presence of similar charges on neighboring particles generates electrostatic repulsion that prevents aggregation and contributes to colloidal stability. For example, ferric hydroxide colloids usually acquire a positive charge through the adsorption of Fe3+ ions, whereas sulfide sols often become negatively charged due to the adsorption of sulfide ions. The distribution of ions surrounding a charged colloidal particle forms an electrical double layer. According to the Stern model, this structure consists of a compact inner layer of adsorbed ions and an outer diffuse layer containing mobile counterions. The potential difference between the moving particle surface and the bulk solution is known as the zeta potential. Zeta potential is an important parameter for evaluating colloidal stability. High positive or negative zeta potential generally indicates stable dispersions, while low zeta potential promotes coagulation and flocculation. When an electric field is applied, charged colloidal particles migrate toward oppositely charged electrodes in a process known as electrophoresis. This principle is widely used in analytical chemistry and biotechnology for the separation of proteins and nucleic acids. Electroosmosis, another electrokinetic phenomenon, involves the movement of the liquid medium relative to a charged surface under an applied electric field. Applications of colloids. Colloidal systems play essential roles in many industrial and biological processes. In the food industry, products such as milk, butter, whipped cream, mayonnaise, and ice cream are examples of colloidal dispersions. Their texture, stability, and appearance depend strongly on colloidal interactions. In medicine and pharmaceuticals, colloidal systems improve the delivery and absorption of drugs. Emulsions, suspensions, and colloidal nanoparticles are commonly used in therapeutic formulations and vaccines. Artificial kidney dialysis systems also rely on colloidal principles to separate waste products from blood through semi-permeable membranes. Water purification processes employ coagulation and flocculation to remove colloidal impurities. The addition of electrolytes, such as alum, destabilizes suspended particles, allowing them to settle. Similarly, electrostatic precipitators remove colloidal smoke particles from industrial exhaust gases. The paint and coatings industry depends heavily on colloidal dispersions of pigments and polymers. Thixotropic paints exhibit reversible viscosity changes because of colloidal interactions among suspended particles. Colloidal processes are also important in textile dyeing, leather tanning, detergents, and cosmetics. Natural phenomena such as cloud formation, fog, smoke, and the blue color of the sky are further examples of colloidal behavior. In conclusion, colloids and colloidal systems represent an important class of materials characterized by finely dispersed particles and dominant surface phenomena. Their unique optical, kinetic, and electrical properties arise primarily from their intermediate particle size and large surface area. Phenomena such as the Tyndall effect, Brownian motion, electrophoresis, and electrostatic stabilization provide insight into the behavior and stability of colloidal dispersions. The principles of colloid science are fundamental to numerous fields, including food science, medicine, environmental engineering, coatings, and materials science. Continued advances in colloid chemistry and surface science remain essential for the development of modern industrial and biomedical technologies.